Hi, welcome back. So today will be our last lecture for this semester, and I think we're going to talk about something new about the generative models, and it's quite related to the previous mixture of Gaussian models. So we will first of all when we talk about the first type of generative models, uh, we'll see a lot of similar equations that we have seen before that describes the uh, PDF function, probability distribution functions from normal or Gaussian distributions. But then in the second type of model, which is, I believe, if you have taken any courses in data mining or big data related courses, it's a very simple but intuitive model. It's called Bayesian model, naive Bayes model. And it's also a typical type of generative models. And the third model we're gonna introduce is the generative adversarial network. Um, in short, it's the acronym is GANS, and it's quite a popular model or popular um, learning techniques or learning uh, machine learning technology that are getting more and more popular recently. Okay, so I hope these uh, lecture that what we're gonna cover today will helps you open up a new door towards a pretty new field, um, because the generative way of thinking of models and data are quite different from the our previous way, our old way of discriminative learning ways. Okay. So for we will discuss more about the final on Thursday's class. So I am preparing the final questions. So yeah, let's have more of that discussion on Thursday. Okay. So let's see this difference of the paradigms between discriminative versus generative ways in conducting supervised learning tasks. I would say so far, all the models we have covered in this course, they belong to the discriminative learning algorithms. And by discriminative learning, by the term discriminative, what we actually means is that we try to classify the data. That is, we given a feature from the data points, we would like to predict a label, right? That is associated to that feature. And so we are actually modeling the probability of the label given the feature, right? It's actually a conditional probability of y given x, okay? So a typical example, logistic regression, we use the outputs from a sigmoid function as the probability that a given data point x belongs to the class y equals 1. Okay, so this is a very typical discriminative learning. We are discriminating data, classify them into different groups. And on the other way, the generative paradigm or the generative learning algorithms actually swaps the sequence of y and x. We map features to labels, right? It's not to classify data, but given a label y, we want to kind of predict the features, but in a slightly different style. We are not trying to predict exactly what feature is, but we are going to model the likelihood of the data, likelihood of the feature X given a label Y, okay? And also, meanwhile, we need to also estimate the priori probability, which is the probability of the feature of the label alone, P of Y, okay? So take a more concrete example, like if our task is to use all the words in an email and to predict whether this email is a spam or not, which is a simple binary classification task. And if we think of it as a discriminative way or a discriminative problem, then we need to um, obtain some probability that tells us how likely an email is a spam, given the words. Like we see the words first, and then we make a guess, like how much percent that email can be a spam. So that is a discriminative way. But if it's a generative way, then we need to think of this problem in a from the different angle. Like assume this, we will ask ourselves, assuming this email is spam, then how likely are these words? Okay, so assuming this email is spam, then how likely um, do I expect to see the word like promotion, um, market, products, and so on, right? So these two paradigms, they are kind of in the opposite directions. Think of the problems in the opposite direction. So let's step more further into this example of mail classification task. Let's use the label y equals 0 for not a spam and y equals 1 for spam mail. So the generative approach basically needs to model the distribution using p of x given y equals 0. So this conditional probability models the distribution for a non-spam mail, right? And of course, the other conditional probability p of x given y equals 1 models the distribution for the spam mails, right? And also we need to model the priority distribution. That is, without seeing any, that is, I would say that is the um, probability. It's like a basis probability um, of the spam versus non-spam mails. Or you can think of it like in the world, how many spam mails are there in total, and how many versus the number of non-spam mails in total. Okay. So a generative approach needs to estimate these bunch of probabilities. It's two conditional probability and a priori probability. And after we have estimated these probabilities using some quantitative methods, then given any new input data, given any new email, then we should use the Bayesian rule to compute the so-called posterior probability. So for the term, this is not the first time that we come across the word posterior. In a mixture of Gaussians, we use the posterior probability, right, for salmon versus tuna. So this time we need to compute the posterior of a new email, which is the conditional probability of y given x, and x is the email, by multiplying the this conditional probability, x given y, and the priority py, and the probability of x, divided by the probability of x. And that is the Bayesian rule. And we can use this to find the correct prediction, or find the most likely prediction for that new input email x. Okay. So actually the denominator, which is p of x, we can get an estimate for p of x by numerate over all possible outcomes. So in this case, it's just two outcomes. It's either y equals 1, either male or non-male, okay? But if we don't compute P of X, that is also okay, right? Because we just need to know, relatively speaking, which one is bigger. Because if P of Y equals 1, given X, say if this one is greater than, if it's greater than the probability of Y equals 0, given X, then we can say that we can conclude that it's more likely to be a span. So the P of X in the denominator term does not necessarily require our computation. Okay. So let's look at several more concrete implementations of generative learning algorithms. So far, I would say on this page, we are still conceptualizing the problem. So we propose a bunch of probabilities, right? But how we estimate this probability, say the probability of a email given a label, that requires some breaking downs of the details, right? We can represent an email with different kinds of features. So this feature vector X, there are a lot of, a whole bunch of possibilities. Like we can use all the words, all the bigram terms, trigram terms, all the, even the dates, the subject words, and so on. So, and we need to figure out different ways to combine those features. So let's look at several, actually 3 types of models that we're gonna cover today. So the first 2 types, the first one, the Gaussian discriminant analysis, or GDA, and the first one, Nalve Bayes, they are actually closer related to the problem we described in the previous slide. Okay, but the generative adversarial network, I would say the example we introduced in this lecture is more about the original work of GANS, which is not about classification tasks, but is about uh, uh, generate interesting or meaningful patterns that are usually in the field of computer vision, like generate a meaningful images out of nothing or out of some random samplings. Okay, so it's not applied to a supervised learning task like predicting spam mail versus non-spam mail, but um, the mathematical principle or the generative thinking is kind of similar. It's like taking some samples from some random data and then generate some more sophisticated data out of these random samples. All right, let's look at the first model, which is GDA. Okay, so it assumes that the likelihood probability or the conditional probability of X given Y has a multivariate Gaussian distribution. Okay, in the previous lecture, we already used this multivariate Gaussian distribution to model clusters in unlabeled data, right? But today, the data we gonna use is labeled, so that'll make things easier compared to the mixture of Gaussians and the EM method. So for a feature that is that has a continuous random values, then and our label is a binary label for simplification. So the GDA will model this conditional probability with a multivariate Gaussian distribution. So for a multivariate distribution, we will need to have a mean value, right? So because Y has 2 outcomes, it's actually 2 probabilities. the probability of x given y equals 0 should has its own mean, right, which is mu 0, and a covariance matrix, right, because it's a multivariance random variable. And for the other probability, x given y equals 1, it should also has its own probability, which is centered around the mu 1 and with some covariance matrices. Okay, and here we assume that they have the same covariance matrix. And the probability, the y itself, the label itself is also drawn from some distribution. And here we assume that the random variable y is also is drawn from a Bernoulli distribution. Okay, so a Bernoulli distribution is a commonly used distribution to describe a binary outcome, either 0 or 1. It's like the probability of tossing a coin. All right, so given these targets probabilities, because we assume that um, the first two ones are from a Gaussian distribution, so we can use the Gaussian, the PDL functions of Gaussian to describe it, right? Remember the equations here, we put the denominants of the matrices here as the denominator, and the inverse of the uh, uh, covariance matrix in the middle, and the mean values here. Okay, and the Bernoulli distribution has this PDF function form, right? So the this is actually a fancier expression by combining two outcomes. If y is 0, then this one is 1, right? And this one is 1 minus 5, okay? So this term simply says that the outcome for y equals 1 is 5, and the other outcome is 1 minus 5, right? So it's a rather simple mathematical expression here. Okay, so given these probabilities, we have a bunch of parameters, right? We have mu's, sigmas, and phi's, and those are the unknown parameters that we need to learn, or we need to fit against the data. Okay, and the goal is to find the best parameters that maximize uh, the posteriors, which is the likelihood of the data times the priori probability. Okay, so let's proceed on to the next slide. We will find very similar forms as those used in the mixture of Gaussian models. Okay, so it's some expansion um, of the previous equations under the condition of two-dimensional data sets, right? Assume that we are consider a two-dimensional data set. So it should look like this in the two-dimensional space. And the shape of covariance matrices will squeeze the contours into different shapes. Okay, so we're gonna maximize the log likelihood like what we did for the mixture of Gaussians. So the log likelihood is the logarithm of the likelihood function. And the likelihood function is just a product of all the uh, probabilities, is the product of the probabilities of all the data points, right? So the log likelihood is the logarithm function applied to this likelihood function. And the likelihood is the product of all the probabilities for all the data points, okay? So if we expand these terms using the Bayesian rules, right? Because here the probability P of x comma y is the joint probability, or the probability from a joint distribution. But by applying the Bayesian rules, we can uh, decompose it into the likelihood and the priori distribution, right? So it also describes the generative process, right? Because the process of observing some data points is like you first determine the y, right? You first determine whether this is a uh, say spam mail or non-spam mail. You need to choose y equals 1 or 2, or y equals 0 or 1. And after you determine the y, you need to draw a data point x from um, either Gaussian distribution. Okay, so we decompose the joint probability into the uh, products of the priori and the likelihood. And the likelihood is in the form of the Gaussian PDF functions, right? We just plug in all the uh, uh, equations here. And also the priori also follows as the Bernoulli distribution because we define that, right? We use the phi to describe the Bernoulli distribution, okay? Now we're gonna apply the similar trick by applying the logarithm to a product. Basically, it will turn into a summation, right? It turn into a summation of a pretty long terms. But since there's an exponential terms here, um, we will remove this exponential function, right? Because it eliminates with the logarithm function, but the logarithm function with phi remains here, right? These two terms is quite similar, right? It's quite familiar. I mean, it looks very familiar to the logistic regression results, logistic regressions um, uh, cost function, right? So now we want to um, take the derivatives of this log likelihood function with respect to all the parameters, right? Including phi and mu's. So we'll start with phi, right? So if we take derivative with phi, it will give us a pretty neat term because all the a logarithm function will be gone, right? So if we make the derivative to 0, then we can basically solve these equations by this way, which means that the phi can be can have a really clear analytical solution, right? Which is the summation of all y's divided by the number of all data points, right? If we indicate it by a indicator function, use an indicator function, right? So it's actually, think of the meaning of this equation. That is to simply count how many ones are there, right? Among the total training data sets, how many ones are there? And we use the ratio of those ones as an estimate for the priori probability phi, right? That makes sense to us because the training data set is all we've got. So we need to use the distributions of the, we can simply use the counts of positive examples as the priori probability estimation. Okay, so for phi, it's quite easy to get. Okay, and for the other parameters, we need to separate mu equals 0 and k equals 0 or 1 because it's two outcomes. So we'll do the same thing by taking the derivatives with respect to mu k. We will have such a form of summation, right? And we will do some simplification, and which can tell us the solution that the mu k will be the weighted summation of all data points. Okay, so for mu 0, it will be the weighted um, average among all the data points that has labels y equals 0. And for mu 1, it's the average value for all data points that has 1, label 1. So these are all very intuitive solutions, right? Because, and also it's, I hope this may connect you back to the mixture of Gaussians, to the mixture of Gaussian methods. And here, those ones are all indicator functions, okay? So the mu1s and mu0s can be easily estimated, and so does the other uh, covariance matrices. So it should be the weighted summation. Uh, so um, it's the variance among all the data points that are belong to certain labels. So given these solutions, that means we have modeled the data with two Gaussian distributions with mu's and sigmas that are clearly uh, defined by the data, that are purely defined by the data. Okay, so if we plot these two Gaussian distributions, it'll be like this. If we plot the contours, okay, it'll be quite um, um, neat visualization. So if we uh, visualize this in a 3D space, then we will see two peaks, right? Basically, the one peak groups at the center of the positive examples, and the other peaks centers around the negative examples. And for any new data, we can compute the posteriors using the mu, sigmas, and the phi's, and then we select the class that gives us the higher posterior, right? So this straight line in the middle is the decision boundary. So towards the left side, upper left, the lower left half, if you watch these data points, oops, for example, these data points, they have higher uh, posteriors that makes them belongs to this class, to the cross, right? But for these, maybe for these 2 points, although they are nearing the middle, but near a decision boundary, but by computing the posterior probabilities, they belong to this circle class, okay? So the parameters now we have very clear um, meanings from the perspective of a Gaussian distribution. Okay, the mu describes the centers of the Gaussian, and covariance matrix describes the covariance between the two variables. Okay, so that's so much for the GDA method. Okay, so next we're gonna look at a um, second method, which is naive Bayesian model. And it doesn't actually use the Gaussian, takes the Gaussian assumption because it takes an even more, much simpler assumption that doesn't consider the Gaussian probabilities, the Gaussian properties. Um, and it takes a very naive assumption that if a data point has multiple features, then all these features should be conditionally independent, okay, which is a very convenient assumption in the case, for example, for uh, text-based classification, like we classify an email using all the words, okay? So a typical naive Bayesian model will consider all the features as categorical variables. Say in the spam mail task, classification task, the X is the text body. So X1 to XN are the N words in a email. And the label is also binary, either 0 or 1. Okay. So for example, if we have a email that looks like this way, like dear customer, blah, 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 there's a buy here, products there, okay? So we can construct a vocabulary, right, which may be a pretty big number because that a vocabulary should uh, list all possible words in that are possible to appear in an email, right? So say we can find those words as categorical numbers. as 0 or 1, right? But if we're going to model the likelihood of this email, P of X, given the label y equals 0 or 1, then if we assume the feature vector X is from a multinomial distribution, that is, all these V outcomes, all the V components of this vector has two possibilities, right? Then either appear or not, right? So if I'm going to model X in such a way, then we need to consider 2 to the power of V possible outcomes, which is totally infeasible, okay? So we need to make some simplified assumption of X, okay? And this simplified assumption is called Nalve Bayes assumption. So that says this assumption assumes that all the features, all the words in the case of email are conditionally independent given the label Y. Okay, so that means given the label Y equals 1, which is a spam mail, then whether the word by appears in the email will have no effect on whether the other word product appears. So of course, this is a very simplistic, very simple assumption, which may not be correct, but it does save us time and make it a feasible problem. Okay, and this is a very strong assumption because by the nature of language, we know that the words that appear in the same text, they are kind of more or less related, but not totally independent. Okay, so that's why we say this is a strong assumption. It's for the convenience of computation, but it is not necessarily a truth. Okay, so given this assumption, we can assume that now we can decompose the probabilities of all the words in the vocabulary given Y into a series of products because all the words are independent. So we can use this uh, product between probability of x1 times x2 times xv, right? And so on. So, and we can also use parameters like phi uh, uh, j um, given y equals 0 and phi j given y equals 1 and phi y to describe to describe the probabilities. Okay, so these are the three parameters we need to fit by this model. Okay, and the phi of j given y equals 0, the first two terms are the likelihood of the data, right? Because it tells how likely the word is gonna appear, okay? Given different conditions. And the phi of y is a priori, okay? So we want to maximize the log likelihood of the data, which is the product of a joint distribution, a joint probability of xi and yi. Okay, so let's further look at how we solve this problem. And let's look at the solution first. So we will directly give the solution here. So the probability, the phi of j given y equals 0 is, if you look at the numerator term here, it is the indicator function applies to xj equals 1. And this, it means and. This logical operator means and. So it's simply to count how many times that word, that xj word appears within this non-spam mail class, okay? And divided by the summation of all the total number of non-spam mails. Okay, and if we look at the second parameter, it is the number of the counts, or the number of occurrences that the word I appears in the spam mail, because this time the yi is 1. Okay, and the total, and the denominator is the total number of spam mails. Okay, and the priori phi I is the ratio of spam mails. So this is quite intuitive solutions, quite intuitive solution, because they have clear meanings. All we need to do is to collect all the spam mails and the non-spam mails, and then we within the spam mails we need to count how many times the word, for example, the word buy, how many times the word buy has appeared, right? Versus the count for other words. Okay, so let's but the proof of this is actually quite is not that straightforward. If you're interested, you can um, refer to this link to see the complete solution. Okay, so given the model, given the phi, the two likelihood parameters, and the priori function and the priori probability, we can easily make predictions given this new email. Okay, so given the new email x tilde, we can compute the posterior, which is y equals 1 given x, right? Which is by the Bayesian rule, we need to multiply these two probabilities together, which is likelihood times the posterior times the priori divided by the probability of x p of x tilde. And this denominator, as we have seen this before, it can be the weighted summation of all possible outcomes. So it's the probability of y equals 0 times all possible outcomes of xj in that condition, right? Plus the probability of y equals 1 times all possible outcomes in that condition. Okay, so the denominator is just for the normalization purpose, but we don't necessarily need to compute the denominator if we don't need the actual probabilities. Okay, so let's go through an example. I have listed 2 examples here, but I don't think we have time to go through all of them, both of them in detail. So I will go through the first example just for a demonstration. So let's consider this minimal text classification example, sports versus not. And we have collected a bunch of email examples, samples. We have both, and we assume they are already manually labeled with sports versus non-sports. Okay, and the number of words. Let's count how many words are there in sports. So if we do count those examples, we find that there are 11 words in total in sports, and 11 words in non-sports. There are 9 words, okay? And the total number of unique words, that is the vocabulary size, is 14, okay? So, and the question is, given a new text, for example, it's a very close game, then we need to make a judgment of whether it is sports or not. Okay. All right, so let's do the analysis. We have 2 labels, S and NS, right? So if given the new sentence, a very close game, then our goal is to estimate the posterior, right? That is the probability of spots given this observation, given this a very close game. okay? And these posterior probabilities can be rewritten according to the Bayesian rule, which is the likelihood times the priori, okay? And the likelihood is uh, the probability of the sentence given the label, right? And by the naive Bayes rule, we can think of that these four words, they are independent, right? So we can use the probabilities of the word A given as times the probability of very given as, and so on, okay? And for the other posterior, which is the probability of non-spots given that new sentence, we can also do the similar decomposition, okay? So now things becomes easier. We just need to estimate those individual probabilities alone, right? Like the probability of A given as versus given non-as, right? All these probabilities can be estimated from the data. So, and the easiest way is to use the smoothed word frequencies. Okay, so I listed these numbers here. For example, the article word A has appeared twice in the sports category. So the probability of A given as is estimated by 2 over 11 plus 14. Okay, and this 11 plus 14 is because uh, for the for the normalization purpose. Okay, so and we can do the same thing for all the words in the testing example. Okay, for example, the second word very, it has appeared once in sports, right? So the probability of it will be like this, but it has appeared 0 times in word. We haven't observed it before, so we will give a +1 smooth so that the probability is not 0, right? If there's a 0 in the series of products, it will be a trouble, right? So after we have estimates the word frequencies with these probabilities, we're able to estimate the method like this, estimate the posterior probabilities like this. So our conclusion is that the probability of the posterior of sports given this observation is much higher, right, than the posterior of NS given this same sentence. So our conclusion is that it is more likely to be a sports related topic or sports related category. Okay, so that's a simple example of naive Bayesian models. All right, now let's skip the second example. I hope you can go through the examples yourself um, after the lecture ends. So here in the example, we have more outcomes and more features, but we basically need to convert all the continuous features into categorical ones. Okay. So lastly, let's look at the third type of generative models, which is called generative adversarial network. So as I said before, this is not very closely related to the classification tasks as shown for the previous two examples. But it's a pretty new technique, and it's quite getting more and more popular um, in the field of machine learning in general. And I think the most amazing part of it is that we can train models that can behave like human beings, like can behave in terms of drawing a picture or um, um, say something in natural language, right? In generating natural sentences, okay? So the example we're going to use today is from the original work of the creator of this type of model. That we will is basically from the application of computer visions. Okay, so it's first proposed in 2014 by Goodfellow, and the basic question that it asks is, how do we build machine learning models that can understand the world? Okay, so they operationalize the verb understand by that if a model is able to generate some good data, then we can claim that it understands the word, partially at least. Okay, and a good data, we mean data that are close to human generated data. Okay, so in the case of uh, drawing a picture, then if a model is able to draw a picture that is very close to a real picture, that even a discriminator cannot tell the differences, then we will say that the model that generates the picture is a very successful one. Okay, so given that mindset, first we are going to the GANs actually implement two neural network based models. The first one is the generator, who is in charge of drawing the pictures. Okay, and the discriminator, whose role is to tell whether the picture drawn by the generator is a fake or real. Okay, so so it's actually two models that we need to train. Okay, and the models painted here in blue color is the generator, and it takes some random inputs. So this z can be a random vector, and it's feed this random vector into some um, reversed version of CNN. It's like we enlarge the random input to some fake images. And these fake images will be compared with the real data judged by the discriminator. And this discriminator will tell whether the generated data is authentic, is real or fake. Okay. And on this slide, it is pretty a simple technique, right? But actually, we'll see that having a GAN successfully trained is not an easy task. Okay, so for example, if our uh, task is to generate human-like handwritten digits, okay, so the generator will take some input purely from random noise. So there's no information at all at the beginning. So it will generate some fake images at this step, and the fake images will be compared with the real images from the training set. And the discriminator will make such a comparison and generate make the predictions of whether this is real or fake. Okay. So, and the discriminator uses a regular convolutional CNN, but the generator it needs to take some small inputs and gradually grow that inputs into a larger but thinner images. So which is a reverse version of the convolutional neural network, which we can call it deconvolutional neural network. Okay, and nowadays we already have very convenient implementations of this uh, deconvnet in mainstream machine learning frameworks. Okay. Okay. So the training process, if we describe it with mathematical language, we can think of it as drawing examples from distributions. say the random input Z is from a distribution P of Z associated with the probability of P of Z, right? And the generator will take the Z of inputs, and the theta of G is the parameters involved, is all the parameters involved in the DConvNet models, okay? So the generated data, let's assume that it's also from some distribution P of G, and this lowercase g is for generator, okay? And the real data is from the training data. So we say that the distribution is described by P of data, okay? So, and the discriminator also comes with a parameter theta of D, okay? So the output of the discriminator is the probability that X came from P data rather than the fake distribution P of G, okay? And the training for the discriminator is to maximize the logarithm of D of X. But the training process, the cost function for G is to minimize. The goal of training the generator is to minimize the logarithm of 1 minus D of G of Z. Okay, so this is a bit tricky part here. So because the generator is, the goal of training a generator is to fool the discriminator, right? We want the difference between the generated output to be as close as the as close as the real data. So we want the D of G of Z to be as big as possible. Okay. Let's go to the next slide. Yeah, oh, right, it's in this slide. So mathematically speaking, we are the whole training process is a minimum maximum gain. So it's like a cat mouse game. So we want to grow the discriminator, right? But we also want to grow the generator. And the generator, the role of generator is to fool the discriminator. And if the discriminator is too strong, say each time, as long as the generated output is a little bit fake, the discriminator can tell the difference. Then that means the generator will pick up no information. It will never learn, okay? And if the discriminator is too weak, that it doesn't tell any difference between a real and fake, then the generator also cannot grow too much because it's realized that, okay, I can uh, randomly generate some meaningless information, and that will fool the discriminator. So anyway, the training process is very tricky for training a GAN model, okay? So if we illustrate so these figures are from the original paper. So if we illustrate the training process, the green curve is the distribution of the generator's output. And the dashed line in black is the real distribution of the data, okay? And the dashed blue line is the discriminator's performance output. So at the beginning, so the difference between you can see two peaks, right? The dotted black peak is the real data. The green one is the fake data. So at the beginning, they are apart from each other. The two fakes don't overlap. And as we first train the discriminator, okay, after we train the discriminator can clearly tell the difference between the real and fake, okay? But so far at this step, we didn't train the generator yet. We first train the discriminator, okay? And after we train the discriminator, we will start training the generator. And the training a generator will gradually move the distribution of the fake data towards the real data, which will eventually make the two distributions overlap, totally overlap. And in that case, because the two distributions, they perfectly overlap each other, then the discriminator can no longer tell the differences between them. Okay. So that's why eventually the blue dashed line becomes a flat line. It doesn't tell the difference between the two distributions at all. Okay. All right. And the training steps is quite tricky. And nowadays, we have developed, people have developed various types of GAN-based technique to make the training process more stable. Um, so but the basic idea is that we need to train a discriminator first on real data and then generate fake data using the generator and train the discriminator on the fake data. Okay, but when we train um, discriminator, the generator is phrased, and when we train the generator, the discriminator is frozen. Okay, and we'll repeat these steps for several epochs until the fake data seem legit or seems acceptable. And that requires some human knowledge. We need to look at the data ourselves, look at the generated output ourselves. So, for example, in the initial work from Goodfellow, they use uh, in the handwritten digit example, all the pictures here highlighted by the yellow frames are generated data. Okay, so they are very good generated data that looks pretty authentic, right? They are animals face, human faces, and the handwritten digits. And the results from now the more recent years are even better. There's several websites that describe the data sets. um, I think the name is called the "This Human Doesn't Exist." If you search it on Google, you will find the data sets. You will find a website that describes human faces that are really real. That's no different from a picture, but these are the fake data generated by a GAN model. Okay, and we can use it to generate artwork, portraits, landscapes, and a cooler information is like we can use the um, generator's output to conduct image arithmetic operations. Like we can uh, use like the representations for smile as the hidden representation. And if we based on the smiling expression and minus the gender neutral gender of woman and plus the gender plus the man as another gender, another dimension of the gender, then we will have a smiling man. So similar features can be captured by the GAN network. Okay, and the example I show here is showing the another effect or another function for applying GANs. It is has an interesting application in style transfer. That is, the GANs we learned from different data sets can generate different styles of paints, and the intermediate representations from those different GANs can be used to apply a switch between of the same picture switch to let it switch between different styles. Okay, like the seasons can be a style, or the genres of a paints can also be a style. Okay, yeah. So so far the GANs face several issues with stability and how to really train a GAN work that's without fail too much, because the um, discriminator and the generators, they depend on each other. So the system is very unstable during the training process. If you train one network doesn't train one network properly, the other one may fail. Okay, because uh, they rely on each other very closely. They are closely coupled systems. Okay, so we have done with the last lecture topic, which is generative models today, and I would say the take-home message is that it's quite a different style of machine learning technique. So the first type of works, they are based on supervised classification tasks. And the last type is to generate human-like data from purely unsupervised data. But the way of they share the same way of thinking, which is to um, generate or generates the data that can be described by the likelihood of the data given some labels, given some classes of the data, right? So I think the GANs we can um, you can search for more information if you're interested, because the slides that I'm showing here is based on the original work. And I think in recent years, people in that field have gained more uh, breakthroughs in training effective GAN models. Okay, and that's so much for today. And we will meet again on Thursday. And we will talk about the time and the forms, and we will review the contents for the final exams.